So what we are discussing here are the well-known power law that are exhibited by several features measured in cities. And here is a very important work by Louis and Dirk that is one of the pillars in this field, and probably was also my starting point to study this topic. And so everyone knows now, after these very relevant studies, that many features for urban cities, are regulated by power laws with exponents that depend on the different features. So for socioeconomic feature like GDP, patents, innovation, and many others, the exponent is greater than 1. And for individual needs that are water supply, waste gathering, so activities that are not related to interactions among individuals, the exponent is about 1, is found quite exactly close to 1. And for physical infrastructure like transportation or any other similar infrastructure, water supply, the water network supply, not just the individual consumption, the exponent is smaller than 1. So starting from this very general universal behavior, we did a few studies. One recent study was related to the full Italian territories. We analyzed 107 Italian metropolitan areas over 20 years. So we built a database of features that are collected for each of the metropolitan areas. So you can see here in the north, Milano, the Milan metropolitan areas, which is quite dark, and Torino, larger, and so a bit less dark than Milano. And we have Bologna and Rome, and so you can see the main area of the Italian country. So we collected all the data from the public open access data collection of the Ministry of Statistical collection data in Italy regarding the population. And we collected the patents from a private server that is the very famous, I don't remember now, but this is the, the Orbit Intelligence provider for patents. That is a private provider, but compared to the Google or other provider of patent, this collection of Orbit Intelligence gives the location of the patents. So the location of the patents, where it is produced, where it is issued, it is given by a specific feature. So we collected this data, and for the same territory, we collected also the recycled waste fractions for the same 107 metropolitan areas of Italy. So what we found for these 20 years of data are, yes, finally, we found the scaling laws that everybody here, Dirk and Louis in particular, they know well. And so, yeah, we were happy that actually the patents were scaling with an exponent that, as expected, was larger than 1. And it was, okay, the laser pointer is not so efficient, but anyway, you can see that the power law is reported for 3 years of the 20 years that we investigated. So the first year is the 2001, and then we have 2010, and finally, in the third panel, we have 2020. So as you can see, the exponent is larger than 1, much larger than 1, and increasing over time. There is a lot of noise around this regression line. And, but nevertheless, the dispersion is more or less constant over the years. So there is a standard deviation of 0.19, 0.18, more or less the same. Contrarily to the patents, the recycled waste material show a linear, more or less linear behavior as expected, because the recycling activity is an individual need. So everyone recycle the waste according to their own habits. And so there is actually not much interaction, but yes, then we have more or less an exponent about 1, just larger than 1. And then this exponent decreases over time. And in 2020, for the data collected for the last year of the 2 decades, the exponent beta was almost exactly 1. This indicates that there is an improved behavior towards recycling, and also this is indicated by the diminishing dispersion around this regression line. So, but yeah, there are anyway many things that can be said about this behavior, because first of all, the patenting attitude of a country, of the metropolitan areas, is not a controlled system. And so more or less the innovation in company or in a small university that are doing patenting is, let's say, a free initiative. So it is not controlled by the outside. And also the data are, let's say, certified data in the Orbit Intelligence Service, but for the recycled waste, despite this is the national collection of data regarding the recycling material for Italy. So these are the data provided by the Ministry of Health, of Environment through the ISPRA group of research on recycling waste. So these are anyway provided by the administration to the ministry, so there is not an automatic collection of data. So we never know what is the precision of this data, and so probably with an automatic waste recycling service, this would be more meaningful. Anyway, this is meaningful for policy reason, because what does it mean that the recycling is working so well, that the people are really taking into account the necessity, the importance of recycling the material correctly, or it is a not so, let's say, precise way to provide the data. So there are many issues that can be discussed regarding the different behavior of this curve. So the main take-home message is that this kind of studies and analysis of big data over many decades of collecting data are really powerful for policy making that might expect some very informative behavior from this exponent. Okay, so this might be interesting, and it is indeed interesting for the policymaker. Okay, so these are the table collecting all the data for patent families, patents, and recycled material. So I don't want to bore you with this number that are more or less confirmed by what we discussed before. And also we have data for every fraction of recycled waste that might be interesting for other purposes. But anyway, this is just a first introduction of this research that we are conducting now in the context of a national initiative that was funded by the Ministry of Economic Development of Italy. And so this research was done in cooperation with the Agenzia of Italia Digitale that is in Rome, that I didn't mention before, and with the University of Genova in Italy and the University of Castellanza also in Italy. So it is a joint research program. Okay, so now we have discussed, we have understood that this exponent might be interesting for understanding and envisioning the behavior of many activities over the different metropolitan areas. But it is important, we learn by our giants in this room, that this exponent have a microscopic origin that can be modeled. And here we have a model presented by Luis in order to justify the values that are taken by this exponent. In particular, Luis is here, he can correct me. The main idea behind the model, the analytical model, is related to the probability of interaction between different individuals in a city. And this probability of interactions is affected by the heterogeneity of the urban structure. More or less should be this the idea. And so this central concept was the basis of several calculations that are reported in this and other paper. And the final results in this work was a relationship that is symmetric between the exponent for the infrastructure, the one that is lower than 1, and an exponent for the social interaction that is larger than 1. So the sum of the two exponents is equal to 2, and this was obtained also in the previous experimental work. This is confirmed by the experiment. So after, there are many models that have been proposed to reproduce this exponent and justify the origin of this behavior, but more or less they are always related to the random infrastructure of the urban area. So in this slide, we have another model that was proposed by Fabiano Ribeiro and co-workers that is based on a gravitational concept, similar gravitational model that is included in this exponent, the gravitation terms, but nevertheless there is also a probability of interaction. Oh, I was so slow. that again contain the fractal dimension of the cities. And this is the last one. So now the last one will be described very quickly. And this is again related to the fractal dimension, but they consider Carlos Molinero and Stefan Turner, that unfortunately is not here. They consider a three-dimensional structure, so they include the third dimension of the building, and they derive some other exponent. Okay, so we then ask ourselves, okay, what is the correct model and how to understand this? So we started to have some graphical representation. And so the top one is the Lewis model. Then we have the Fabiano Ribeiro. And finally, the Stefan Turner model, that is the three-dimensional cloud. So there is a general behavior of the scaling exponent against the fractal dimension that is, as you can see, the exponent, the socioeconomic exponent decrease and the infrastructure exponent increase as the fractal dimension of the urban area decrease. So this means practically that for very long urban structure, very linear structure, expanding over a line, the infrastructure will be more costly and the social interaction will be more difficult because they occur over a line. So more or less, this is the meaning of the decrease of the decrease of the beta against the df and the opposite increase of the other exponent. In the Ribeiro model, that is the blue model, as you can see, there is one special point that is obtained for fractal dimension of the city equal to 1.5 that correspond to a completely random organization of the city. And so in this case, as you can see, the two exponents coincide with each other. That means that the interaction over the structure are randomly ruled. And finally, we have an opposite behavior of this law by the Stefan Turner and co-worker. Okay, then we decided to start measuring the fractal dimension of cities. And so we downloaded a few images from the Worldview European Cities collection of the European Space Agency. And we start measuring the fractal dimension. Then we said, if this is so important and so, let's say, discriminating between the different models, let's start this activity that will never end because they collect many and many images. And so okay, you can see here the collection of the cities. Everyone can download these images. And so you can see here one of the Torino Worldview images. Then, of course, we have Zurich as a second example. And so one can download these satellite images and then start to analyze the fractal dimension of the satellite images. First of all, we have to identify exactly the same region that we want to analyze. There are several images taken by the satellite at different times for the same region, and so it is important to identify exactly the geographic position. So we divided the images in a square area. The previous one was Torino, and this is the more crowded area of Torino. And this is Zurich. Northern is part of the lake. And we applied an algorithm that I proposed a few years ago. to measure the fractal dimension of arbitrary dimension fractals. That is summarized in this equation that I don't want to describe because I have no time. Anyway, we can obtain the Arst exponent that is related to the fractal dimension of the cities for every area that is imaged by the worldview satellite of the European Space Agency. So, and finally, we obtain the experimental value of the beta S and beta I as a function of the fractal dimension. And so this was done for several cities. And this is an indicator of the heterogeneity of the different area of the same cities and might be used to reproduce the overall results for the metropolitan areas of the cities that have been analyzed. I'm sorry that I've taken more time than I was allowed, but I hope that was interesting despite the very quick conclusion. And thank you very much for your attention.
Thank you.